This scene deals with the subject many fathers find so difficult.
Welcome to Podcast VE 0.1, where we break down the latest research and tools for curious engineers. Hey everyone, and thanks for tuning in. Remember the discussion a while back when Kubernetes officially dropped direct Docker support in favor of runtimes like containered? It sparked a lot of conversation about the Docker shim component being removed. Well, what if some researchers decided to put that transition to a performance test? Imagine going back into a modern Kubernetes setup, specifically modifying it to bring Docker back alongside containered, just to see which one actually performs better under intense conditions, particularly when pushing serverless workloads right to their breaking point. That's the fascinating premise of a recent paper we're exploring today. It's titled Kubernetes in Action, Exploring the Performance of Kubernetes Distributions in the Cloud, authored by Hossein Akasizadeh, Ehsan Atayeh, and Mostafa Bastam from the University of Mazandaran. As software engineers working with containers, we know that setting up Kubernetes involves navigating a complex stack. It's not just about choosing Kubernetes itself. Which distribution fits best? The standard bootstrapping tool, kubeadm, a lightweight option like K3s or micro K8s, or perhaps the newer K0s. Then there's the container runtime, the low-level component that actually runs the containers. Containered is the default now, communicating via something called the Container Runtime Interface, or CRI. But is it always the optimal choice for every single workload? And we can't forget the foundation. If you're running on virtual machines, does the underlying hypervisor configuration matter? This paper systematically tackles this complexity. The researchers didn't just focus on one piece. They benchmarked the entire chain, starting from the virtualization layer. They conducted their experiments on Cloud Lab, a flexible cloud computing testbed often used for research, specifically using the Xen hypervisor. Xen offers different virtualization modes. There's hardware virtual machine mode, or HVM, which allows running unmodified operating systems by emulating hardware. Then there's paravirtualization, or PV mode, where the guest operating system is slightly modified to cooperate with the hypervisor, often resulting in better performance due to reduced overhead. While Cloud Lab typically defaults to HVM, these researchers actually developed a new profile to enable Xen PV mode for their tests. Their very first step, using disk benchmarks, was to determine which Xen mode performed better in their environment. They found PV mode offered advantages, so they used that as the foundation for all their subsequent Kubernetes experiments. This highlights an important point right away. Optimizing the base layer matters before you even get to tuning Kubernetes itself. With Xen PV mode selected, they moved on to the container runtime question, Docker versus containered. Kubernetes began phasing out the Docker shim, the built-in adapter allowing the kubelet component to talk directly to the Docker engine, around version 1.20, fully removing it by version 1.24. The standard approach now relies on runtimes like containered that directly implement the CRI, the standardized plugin interface for container runtimes. The rationale was architectural simplification and removing maintenance overhead, but did this automatically guarantee superior performance across the board? To answer this empirically, the researchers did something quite notable. They took Kubernetes version 1.27.2, a version released well after the Docker shim's removal, and deliberately modified it. They re-enabled Docker as a runtime option alongside containered, allowing for a direct, head-to-head comparison within the same modern Kubernetes version. This wasn't about comparing an old K8/Docker setup to a new K8/containered one. It was about bringing Docker back into the contemporary environment for a fair performance fight. How did they compare them? They used two different workload types. To stress disk I/O, they deployed a MySQL database inside Kubernetes and used Sysbench, a well-known system benchmarking tool, to generate load. This tested how well each runtime handled storage-intensive operations. To stress the CPU and container management, they used OpenFaaS, a popular open-source function-as-a-service, or FaaS platform, that runs on Kubernetes. Serverless workloads, especially during rapid scaling, can heavily tax the CPU and the runtime's efficiency in starting, stopping, and managing containers. By running OpenFaaS, they could evaluate how Docker and Containerd handled these compute-heavy tasks. The paper states they performed these comparisons to determine the appropriate runtime for the next phase. The key takeaway here isn't necessarily which one won in their specific tests. The provided text focuses on methodology, but the very act of performing this rigorous, direct comparison in a modern context. It challenges us to look beyond the default and consider that performance nuances might exist depending on the workload, even if Containerd remains the standard for architectural reasons. Having established their preferred Zen mode and compared the container runtimes on that base, the researchers then focused on comparing 4 different Kubernetes distributions. First, kubeatom. While technically a tool for bootstrapping clusters rather than a full distribution, it represents the standard, community-driven way to set up Kubernetes. Second, K3s, a popular lightweight distribution from Rancher, now SUSE, designed for resource-constrained environments like Edge or IoT by stripping out non-essential components. Third, micro K8s, another lightweight option, developed by Canonical, the company behind Ubuntu, also targeting simplicity and small footprints for development, testing, and edge use cases. Fourth, K0s, a newer distribution from Mirantis, aiming for simplicity and modern architecture, distributed as a single binary. Critically, for a fair comparison, they used the exact same Kubernetes version, 1.2.7.2, for all 4 setups. They also standardized the networking layer. Kubernetes networking relies on plugins implementing the Container Network Interface, or CNI, specification to handle pod communication. Even though some distributions bundle their own CNI, the researchers manually installed Calico, a popular CNI plugin, across all test clusters to ensure consistency. Their cluster architecture consisted of 1 master node and 3 worker nodes, all running Ubuntu Server 20.04 on those XenPV virtual machines. They also employed a dedicated, separate node solely for generating the test load and collecting measurements, a crucial best practice to avoid the testing tools interfering with the system under test. They used Helm, a package manager for Kubernetes, to ensure OpenFaaS version 0.26.4 was deployed consistently across all distributions. So how did they push these 4 Kubernetes setups? They deployed OpenFaaS onto each cluster, using it as the representative compute-intensive workload. For the load testing itself, they used Grafana K6, a modern load testing tool. Importantly, they didn't just measure average performance, they specifically employed K6's breakpoint testing feature. A breakpoint test is designed to find a system's limits. It works by progressively increasing the load, the number of virtual users or requests per second, in stages, pushing way beyond normal operating levels until the system starts to fail, showing high error rates or unacceptable response times. The goal is not just to find the peak throughput, but to understand how and when the system breaks down. Does one distribution handle overload more gracefully? Do they fail in different ways? This use of breakpoint testing is particularly valuable. It offers insights into system resilience and failure characteristics that simple average load tests might miss. For engineers responsible for reliability and capacity planning, understanding these breaking points and failure modes is critical. So let's summarize the key takeaways for us as software engineers from this research methodology. First, Kubernetes performance is multifaceted. You need to consider the whole stack. The underlying virtualization, the container runtime, and the distribution itself all play a role and can interact. The paper's layered approach reinforces this. Second, the Docker versus Containerd comparison, especially modifying modern Kubernetes to enable it, is significant. While Containerd via CRI is the standard path forward for good reasons, this research serves as a reminder that performance differences might exist for specific workloads. It encourages deeper understanding rather than blindly accepting defaults, even if sticking with Containerd is usually the most practical choice. Third, the choice of Kubernetes distribution, kubeatom, K3s, micro K8s, K0s, can influence performance, especially under extreme load and near failure points. The breakpoint testing approach is key here. Understanding how these different distributions behave under stress, potentially revealing differences in bottlenecks or resilience, is often more insightful than just comparing peak request rates. Fourth, context is everything. These findings come from Cloud Lab using XenPV. Running the same tests on a public cloud like AWS, GCP, or Azure using their prevalent KVM-based or custom hypervisors might yield different results, particularly for the virtualization layer comparison. Performance nuances could also shift based on the specific cloud provider's infrastructure. Fifth, the workload matters immensely. This study focused heavily on OpenFaaS for the main comparison. The performance rankings and bottlenecks observed might change significantly if the primary workload was different. Say, large stateful databases, a different serverless framework like native, or network-intensive applications. The results are most relevant to similar fees or compute-centric stateless workloads. So what's the practical implication for engineers? This paper reinforces that optimizing Kubernetes requires understanding the entire system. Defaults provide a good starting point, but they might not be optimal for every specific use case. The deliberate comparison of runtimes encourages critical thinking about our tools. And the focus on breakpoint testing emphasizes knowing system limits and failure behaviors, not just average performance. Choosing a Kubernetes distribution involves trade-offs that extend beyond just features and resource footprint into how the system behaves under duress, which is closely tied to your specific application's profile. This research provides valuable data points and a robust methodology, encouraging us to take a more empirical, evidence-based approach when designing, tuning, and operating our Kubernetes clusters.